I want to tell you something that might upset you. The key to science, the real key, the thing that makes science work, is something most people get completely backwards. They think science is about finding the truth, about proving things, about being certain. They're wrong. I've spent my entire life doing physics. I won a Nobel Prize. I've worked on some of the most fundamental problems in nature. I've taught thousands of students. And if there's one thing I can tell you with absolute confidence, it's this: science is not about being right. It's about being wrong. More specifically, it's about being willing to be wrong. It's about doubt. Now, I know how that sounds. You're thinking, wait a minute, Feynman. Science gave us computers, medicine, space travel. Science works. How can it be about being wrong? Let me explain. The first principle of science, the absolute first principle, is that you must not fool yourself. And you are the easiest person to fool. I learned this very early. Not in graduate school, not in college. I learned it when I was a kid, watching my father teach me how to think. He taught me something that most people never learn: the difference between knowing the name of something and knowing something. We'd go for walks in the Catskill Mountains. Other fathers would teach their kids the names of birds. "That's a brown-throated thrush," they'd say proudly, and the kid would remember it and feel smart. My father would point to a bird and say, "See that bird? It's a Spencer's warbler." Then he'd pause. "Well, in Italian, it's called a Chutolapitida. In Portuguese, it's a Bomda peda. In Chinese, it's a Chung Long Ta. And in Japanese, it's a Katano Takeda." Then he'd look at me. Now, you know in all those languages what that bird is called, but you still don't know anything about the bird. You only know what people call the bird in different places. "Now," he'd say, "that bird, when it sings, it teaches its young to fly. It flies for hundreds of miles in migration." You see what he was doing? He was teaching me the difference between knowing the name of something and actually understanding something. And that difference, that distinction, is at the heart of what science really is. Science is not about memorizing facts. It's not about accumulating knowledge like you're filling up a bucket. It's not about being able to recite what other people have said, no matter how smart those people were. Science is about questioning. It's about doubting. It's about saying, "Wait a minute, how do you know that? Show me, convince me, and even then, I'm going to check it myself." The key to science is doubt, and most people, even people who claim to love science, get this exactly backwards. They think science is about believing scientists. They think it's about accepting what the experts say. They think it's about certainty, but that's not science. That's religion. Let me tell you what happened at Los Alamos when we were building the atomic bomb. I was young, 24, 25 years old, and I'm sitting in these meetings with some of the smartest people in the world: Niels Bohr, Enrico Fermi, Hans Bethe. These were giants. These were people who had revolutionized physics. And I realized something. These people, these brilliant, accomplished people, they made mistakes all the time. They'd propose something. Someone would show them they were wrong. They'd go, "Oh, you're right. I was completely wrong about that." And that was fine. That was normal. That was how it was supposed to work. The ones who got in trouble were the ones who couldn't do that. The ones who got attached to their ideas. The ones who confused their reputation with the truth. I learned something crucial there. In science, you can't care about being right. You have to care about finding out what's actually true, even if it means you were wrong. Especially if it means you were wrong. So why is this so hard for people? Why do we naturally want certainty? Why do we want to believe that we know things, that we understand things, that we've figured things out? I think it's because uncertainty is uncomfortable. Not knowing is scary. Admitting you might be wrong feels like weakness. But here's the thing. Nature doesn't care about your comfort. Nature doesn't care if you're scared of uncertainty. Nature is what it is, whether you like it or not, whether you understand it or not. And nature is weird. Nature is stranger than you can imagine. The universe doesn't operate according to your intuition. It doesn't work the way you think it should work. Take quantum mechanics. Please, take it. I don't want it. No, I'm joking. But seriously, quantum mechanics is absurd. Particles that go through two slits at once. Electrons that have no definite position until you look at them. The whole thing is crazy. And people say to me, "I don't believe in quantum mechanics. It doesn't make sense." And I tell them, your belief is irrelevant. Quantum mechanics doesn't care if you believe in it or not. It's not a religion, it's not a philosophy. It's a description of how nature actually behaves, and we've tested it to 10 decimal places. It works. The question isn't whether you believe it. The question is, can you accept that nature might work in a way that seems impossible to you? This is what I mean by doubt being the key. Science isn't about constructing a world view that makes you comfortable. It's about letting nature tell you how it actually works, even if that's uncomfortable, even if that challenges everything you thought you knew. Let me give you another example. For thousands of years, people believed that heavier objects fall faster than lighter objects. It made sense. It seemed obvious. Drop a rock and a feather, the rock hits the ground first. Case closed. Except Galileo said, "Wait a minute, let me actually check that. Let me think about this carefully." And he realized the only reason the rock falls faster is air resistance. If you remove the air, they fall at the same speed. And he was right. We can do that experiment now. We can drop a bowling ball and a feather in a vacuum chamber. They hit the ground at exactly the same time. But for 2,000 years, people didn't check. They just believed Aristotle. They believed it because it seemed right, because a smart person said it, because everyone else believed it. That's not science. That's just repeating what someone else said. Science is when you say, "I don't care who said it. I don't care if everyone believes it. I don't care if it seems obvious. Show me. Let's test it. Let's see if it's actually true." And this is hard. This is really hard, because it means you can never completely relax. You can never say, "Okay, we've figured this out. We can stop questioning this." I'll tell you something about physics. We have theories that work incredibly well. Quantum electrodynamics, the theory I won the Nobel Prize for, it predicts things to incredible accuracy, 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. But here's the thing. I still don't fully understand it. Nobody does. We can calculate with it. We can predict with it. It works. But do we really understand why nature behaves this way? No, not really. And that's okay. That's science. Science isn't about achieving perfect understanding. It's about building better and better approximations. It's about saying, "Okay, this is our best description so far, but we could be wrong. We're probably missing something. Let's keep looking." The day you stop questioning is the day you stop doing science. Now, this attitude, this insistence on doubt didn't just appear out of nowhere. It has a history, and it's a shorter history than you might think. For most of human history, knowledge was about authority. You knew something was true because someone important said it was true. The church said it. The king said it. The ancient philosophers said it. That was enough. And if you questioned it, that was dangerous. That was heresy. That could get you killed. Giordano Bruno was burned at the stake in 1600 for suggesting that the stars were distant suns with their own planets. The church didn't like that idea, so they killed him. Galileo was forced to recant his support of heliocentrism, the idea that the earth goes around the sun. He had to say he was wrong, even though he knew he was right. He spent the rest of his life under house arrest. This was the world before modern science. Knowledge was about belief, about faith, about accepting what authorities told you. The scientific revolution changed that. Not all at once, gradually, but fundamentally. People like Galileo, Newton, and many others started saying, "We don't care what the authorities say. We care what nature says." And we're going to find out what nature says by looking at it, by experimenting with it, by measuring it. This was radical. This was revolutionary. This changed everything. But here's what's interesting. Even as science became more powerful, even as it gave us incredible technologies and deep understanding of nature, people kept trying to turn it back into a system of authority. "Scientists say this," they'd proclaim. "Scientists have proven that." And that's not how it works. Science isn't a collection of facts that scientists hand down from on high. Science is a method. It's a process. It's a way of questioning and testing and checking. When I was at Los Alamos, I saw this firsthand. We were doing calculations for the atomic bomb. Incredibly important calculations. If we got them wrong, the bomb might not work. Or worse, it might work differently than we expected. So we'd do a calculation, then someone else would check it using a different method, then a third person would check both calculations. We were constantly checking each other, constantly questioning each other, and nobody got offended. Nobody said, "How dare you question my calculation? Don't you know who I am?" Well, actually, there was one guy who got offended, and we stopped trusting his calculations. The point is, in real science, questioning isn't an insult. It's a requirement. It's how the system works. It's how we avoid fooling ourselves. I remember one time at Los Alamos, I was doing calculations about the efficiency of the bomb, and I realized something. I realized that if we arranged the material in a certain way, we could get a much bigger explosion from the same amount of uranium. So I went to the weekly colloquium. This was where all the big shots gathered, and I presented my calculation. I was nervous. I was the youngest guy in the room, and I was telling these famous physicists that they'd missed something important. You know what happened? Hans Bethe looked at my calculation, thought about it for a minute, and said, "He's right." Just like that. No ego, no defensiveness, just, "He's right, let's use this." That's science. That's how it's supposed to work. But after the war, something changed. Science became prestigious. Scientists became respected authorities. People started treating scientific papers like they were scripture. And that's dangerous, because science isn't supposed to have scripture. Science is supposed to question everything, including itself. I saw this happen with string theory later in my life. Smart people working on these incredibly complicated mathematical structures, and I'd ask them, "How do you test this? How do you know if it's true?" And they'd say, "Well, it's mathematically beautiful. It's elegant." And I'd say, "That's not an answer. Mathematics is a tool. It helps us describe nature. But nature doesn't care about our mathematics. Nature is what it is. How do you test it?" And they didn't have an answer. And that worried me, because science without testing isn't science. It's just mathematics, which is fine. Mathematics is great, but it's not physics. It's not science. Science has to connect to reality. It has to make predictions, and those predictions have to be testable. Otherwise, you're just playing with symbols on a chalkboard. The moment I really understood this, really grasped what science was and wasn't, came when I was at MIT, right before I went to Los Alamos. I was working on something called the Wheeler-Feynman absorber theory. It was an attempt to understand how charged particles interact with electromagnetic fields. My advisor was John Wheeler, one of the smartest people I've ever known. And we developed this theory. It was beautiful. It was elegant. It explained a lot of things. We were proud of it. Then we started checking it against experiments, and it didn't quite work. The predictions were close, but not exact. Now, here's where it gets interesting. We could have said, well, the experiments must be wrong, or there must be some other effect we're not accounting for, or let's adjust the theory slightly to make it match. And people do that. They get attached to their theories. They want them to be right. But Wheeler taught me something crucial. He said, if the theory doesn't match the experiment, the theory is wrong, period. It doesn't matter how beautiful it is. It doesn't matter how much work we put into it. If nature doesn't agree with our theory, nature is right and we're wrong. This seems obvious when you say it like that, but it's incredibly hard to accept in practice because you've invested time, energy, thought into this theory. You've fallen in love with it. You want it to be true, but nature doesn't care what you want. I've seen brilliant people waste years of their lives defending theories that were wrong. They'd come up with increasingly complicated explanations for why the experiments weren't matching. They'd argue about the interpretation of the data. They'd suggest new experiments that might vindicate them. But they were fooling themselves. And the longer they did it, the worse it got. This is what I mean when I say, the first principle is that you must not fool yourself, and you are the easiest person to fool. You want to believe your theory. You want to be right. You've staked your reputation on it. So your brain starts playing tricks on you. You start seeing patterns that aren't there. You start dismissing contradictory evidence. You start believing what you want to believe instead of what the evidence shows. This is human nature. This happens to everyone, including me. I've been wrong many times. I've proposed theories that turned out to be false. I've made calculations that turned out to be incorrect. I've believed things that weren't true. And you know what? Every single time, it was embarrassing. But every single time, it was also liberating, because once you admit you were wrong, once you let go of the false idea, you can start looking for the truth. Being wrong isn't a failure. Refusing to admit you're wrong, that's the failure. At Los Alamos, we had a saying, "Show me your calculation," not "tell me what you think," not "explain your reasoning." Show me, work it out. Let me check it. Because talk is cheap, ideas are cheap. What matters is whether those ideas match reality. I remember one time, this was during the Trinity test, the first atomic bomb test. There was a big argument about how bright the explosion would be. Some people thought it would be like looking at the sunday. Other people thought it might blind you permanently if you looked directly at it. So what did we do? We made predictions. We did calculations. We estimated. And then we tested those predictions. We set up instruments to measure the brightness. We took precautions based on our best guess, but we also prepared to update those precautions if we were wrong. When the bomb went off, we measured and we found out, and some of our predictions were right and some were wrong, and that was fine. That's how it works. That's science. Not making grand pronouncements about what you believe, not defending your position, not caring about being right, just checking, testing, measuring, being willing to be wrong. The insight, the real insight is this: science isn't about what you believe, it's about what you can show, what you can test, what you can verify. And if you can't test it, if you can't show it, if you can't verify it, then it's not science. It might be philosophy, it might be mathematics, it might be poetry, but it's not science. Okay, so let's get into the details. What does it actually mean to do science this way? What does it mean to make doubt the foundation of your thinking? First, it means you have to have a method. You can't just doubt randomly. You can't just say, "I don't believe anything," and stop there. That's not useful. That's just nihilism. Scientific doubt is structured. It's methodical. It follows a process. Here's how it works. Step 1, make a clear, testable prediction. Not a vague statement like, "I think this substance has healing properties." A specific prediction like, "If I give this substance to rats with tumors, the tumors will shrink by at least 50% within 2 weeks. That's testable. That's specific. You can check whether it's true or not. Step 2, design an experiment that tests that prediction. And this is crucial. You have to design it so that it could prove you wrong. If there's no way for the experiment to show you're wrong, it's not a real test. This is called falsifiability. Karl Popper talked about this a lot. A theory is only scientific if you can imagine an observation that would prove it false. Let me give you an example. If I say, "All swans are white," that's testable. All you need to do is find one black swan, and I'm wrong. And guess what? Black swans exist. I was wrong. But if I say, "There's an invisible dragon in my garage," and then every time you try to test it, I add a new condition. "Oh, it's invisible to cameras too." "Oh, it doesn't register on heat sensors either." "Oh, it exists in another dimension." Then I'm not making a scientific claim anymore. I'm just making up excuses. Real science makes itself vulnerable. It sticks its neck out. It says, "Here's what should happen if I'm right, and if it doesn't happen, I'm wrong." Step 3, do the experiment carefully. Control your variables. Measure precisely. Document everything. And this is important. Try to prove yourself wrong. Don't do the experiment hoping to prove yourself right. Do it hoping to find out the truth, whatever that truth might be. I learned this at Los Alamos. When we did calculations, we didn't just check them to find confirmation. We actively looked for errors. We tried to find mistakes. We'd say, "Okay, what if I made an error here? What if I forgot to account for this? What if this assumption is wrong?" Because finding an error in your own work before someone else finds it is a good thing. It saves you from being publicly wrong later. Step 4, look at your results honestly. This is the hardest part, because if your results don't match your prediction, you have to accept that. You can't cherry pick the data. You can't ignore the results that don't fit. You can't say, "Well, those must be outliers." Maybe they are outliers, but you have to prove that. You have to show why those data points should be excluded, and you have to be honest about it. I've seen people torture data until it confesses. They'll run the statistics 17 different ways until they find one that gives them a p-value less than 0.05. That's not science. That's self-deception. If your experiment doesn't support your hypothesis, you have three options. 1. Your hypothesis is wrong. Change it. 2. Your experiment was flawed. Do it again. Better. 3. There's something more complicated going on. Figure out what. What you can't do is ignore the results. What you can't do is pretend they don't matter. What you can't do is declare victory anyway. Step 5. Let other people check your work. This is crucial. Science isn't a solo activity. You can't just do an experiment in your basement and declare you've discovered something. You have to show other people. Let them examine your methods. Let them replicate your results. This is why we publish papers. Not to show off, not to build our reputations, to let other people check whether we're fooling ourselves. And they will check. Other scientists will try to replicate your experiment. They'll look for flaws in your reasoning. They'll propose alternative explanations. And that's good. That's the whole point. When I published my papers on quantum electrodynamics, other physicists went through them with a fine-tooth comb. They found errors. They pointed out things I'd missed. They challenged my assumptions. And every time, it made the theory better. Every criticism that was valid helped us refine the theory. Every error that was caught helped us fix our understanding. That's how science progresses. Not through lone geniuses having perfect insights. Through groups of people checking each other, questioning each other, correcting each other. Now, here's something important. This process never ends. Even after something has been tested many times, even after it's been accepted by the scientific community, even after it's in the textbooks, you can still question it. You should still question it. Because we might be wrong. We've been wrong before. We'll be wrong again. Newton's laws of motion, they work great for most things, but they break down at very high speeds. Einstein's relativity gives us a more accurate description. Einstein's relativity, it works great for most things, but it breaks down at the quantum scale. Quantum mechanics gives us a different description. Quantum mechanics, it works incredibly well, but we still don't know how to reconcile it with general relativity. There's something we're missing. Each of these theories was revolutionary. Each was tested extensively. Each seemed to be the final answer, and each turned out to be an approximation, a very good approximation, but still an approximation. That's the nature of science. We're always building better and better approximations. We're always refining our understanding. We never achieve perfect knowledge, and that's fine. That's how it should be. The problem comes when people forget this, when they treat current scientific understanding as if it's the final word, when they say, science says X, as if science is some kind of absolute authority that can't be questioned. Science doesn't say anything. Scientists say things, and scientists can be wrong. I've been wrong. Every scientist I know has been wrong. What makes science work isn't that scientists are always right. It's that science has a method for correcting errors, for finding mistakes, for updating our understanding when we get new evidence. But that only works if we keep doubting, if we keep questioning, if we keep testing. The day we stop doubting is the day science dies. So why does this matter? Why am I spending all this time talking about doubt and questioning and being wrong? Because I see what happens when people forget these principles. I see what happens when science turns into dogma, when it becomes about authority instead of evidence, when it becomes about belief instead of testing. I call this cargo cult science. During World War II, the U.S. military built air bases on some Pacific islands. The native people on these islands had never seen airplanes before, but they saw that when the Americans performed certain rituals, they'd sit in control towers, they'd wear headphones, they'd wave sticks on the runway, big metal birds would come from the sky and bring cargo, food, supplies, wonderful things. After the war, the Americans left, but the cargo stopped coming. So the islanders built fake control towers out of bamboo. They made fake headphones out of wood. They waved sticks on the runway. But the planes didn't come, because they were imitating the form of science and technology without understanding the substance. I see this in modern research sometimes. People going through the motions, publishing papers because they need to publish, running experiments because that's what you're supposed to do, using complicated statistical methods because that makes it look more scientific. But they're not actually doing science. They're doing cargo cult science. They're following the forms without understanding the principles. Real science is hard. It requires intellectual honesty. It requires being willing to be wrong. It requires caring more about truth than about your reputation. And that's uncomfortable. That's difficult. It's much easier to just believe things, to accept what authorities tell you, to not have to constantly question everything. But here's the thing. Reality doesn't care about your comfort. Nature doesn't adjust itself to make you feel better. If you want to understand nature, if you really want to understand how the universe works, you have to be willing to let go of comforting beliefs. You have to be willing to accept that things might work in ways that seem crazy to you. Quantum mechanics seems crazy. It violates all of our intuitions. Particles that are in two places at once, events that don't have causes, the universe that fundamentally random at its deepest level. But it's true. We've tested it. It works. Nature is telling us that this is how it operates at the quantum scale. We can either accept that, or we can stick our fingers in our ears and refuse to listen. But refusing to listen doesn't change reality. It just makes us ignorant. This matters for more than just abstract physics. It matters for everything. When doctors test new treatments, they need to follow scientific principles. They need to design proper experiments. They need to be willing to admit when a treatment doesn't work, even if they hoped it would. When engineers design bridges or airplanes, they need to test their designs rigorously. They need to look for failure modes. They need to question their assumptions. When anyone is trying to understand anything about the world, whether it's climate or economics or psychology or education, they need to approach it scientifically, which means approaching it with doubt. Not cynicism, not refusal to believe anything, but methodical, careful, honest doubt. Ask questions, demand evidence, check the reasoning, look for alternative explanations, try to find ways you might be wrong. This is how we avoid fooling ourselves. This is how we actually learn about reality instead of just confirming what we already believe. And it's uncomfortable. It really is. Because it means you can never be completely certain. You always have to hold your beliefs tentatively. You always have to be prepared to change your mind. But that's the price of actually understanding things. That's what it costs to really know rather than just believe. Now, I need to address some common misunderstandings about what I'm saying. When I say doubt is the key to science, people sometimes think I mean, don't believe anything. All knowledge is relative. There's no such thing as truth. That's not what I'm saying at all. There are things we know. There are things we've established with high confidence through extensive testing. Newton's laws work extremely well for most everyday situations. Evolution by natural selection is a fact. We've observed it, tested it, confirmed it in countless ways. The earth goes around the sun, atoms exist. Germs cause disease. These aren't just beliefs. These are conclusions supported by overwhelming evidence. When I say we should doubt, I don't mean we should doubt everything equally. Some things are much better established than others. What I mean is, we should never stop being open to the possibility that we're wrong. We should never treat any scientific conclusion as if it's beyond question. We should always be willing to look at new evidence and update our understanding. There's a big difference between I'm confident this is true based on extensive evidence and I believe this is true and refuse to consider alternatives. The first is scientific. The second is dogmatic. Another misconception. People think science is about being skeptical of everything, but that's not quite right either. Science isn't about blanket skepticism. It's about appropriate skepticism. If someone tells me they've developed a new quantum mechanical calculation method, I'll look at their math and check it against experiments. I'll be skeptical, but open to being convinced. If someone tells me they've discovered perpetual motion, I'm going to be much more skeptical, because that would violate fundamental principles of physics that we've tested extensively. It's not impossible, maybe those principles are wrong, but you'd need extraordinary evidence. As Carl Sagan said, extraordinary claims require extraordinary evidence. That's not being closed-minded. That's being rational. We proportion our belief to the evidence. Here's another nuance. When I say we should doubt, I don't mean we should doubt scientists personally. I'm not saying scientists are liars or frauds or have secret agendas. Most scientists are honest people trying their best to understand nature. What I'm saying is, science isn't about trusting people, it's about trusting the method. Don't believe something because Dr. Famous said it. Believe it because Dr. Famous showed you the evidence, and you can check that evidence yourself, and other people have checked it too, and it all holds up. Trust the process, not the person. I've known many famous scientists. Some were brilliant. Some were wrong about things. Often the same person was brilliant about some things and wrong about others. Einstein was brilliant about relativity, but he never accepted quantum mechanics. He kept saying, God doesn't play dice, but nature doesn't care what Einstein thought God would or wouldn't do. Pauling was brilliant about chemical bonds, but later in life, he became convinced that massive doses of vitamin C could cure everything from colds to cancer. He was wrong about that. Being a great scientist doesn't make you right about everything. Being famous doesn't make you infallible. What makes an idea scientific isn't who proposes it. It's whether it can be tested and whether it survives testing. One more misconception. People think science is just about experiments, but science is also about theory, about mathematical models, about thought experiments, about logic and reason. Einstein developed special relativity largely through thought experiments. He imagined what it would be like to ride alongside a light beam. He worked out the logical implications. Then, later, people did experiments that confirmed his predictions. The experiments were crucial, but so was the theoretical work. Science is a combination of theory and experiment. Theory without experiment is just mathematics or philosophy. Experiment without theory is just collection of facts with no understanding of what they mean. You need both, and you need to be willing to doubt both. Maybe your theory is wrong. Maybe your experiment is flawed. Maybe you're measuring the wrong thing. Maybe you're interpreting the results incorrectly. Always question. Always check. Always doubt. But here's the key. Doubt leads to action. It leads to testing. It leads to looking for better answers. It's not paralysis. It's not, we can't know anything, so why bother? It's, we don't know for certain, so let's find out. That's the spirit of science. So what can we learn from all this? What's the bigger lesson here? I think it's this. The way we do science, the emphasis on doubt, on testing, on being willing to be wrong, that's not just a method for understanding physics or chemistry or biology. It's a method for thinking about anything. Anytime you're trying to understand something, anytime you're trying to solve a problem, anytime you're trying to figure out what's true, you can use these principles. Don't just accept what you're told. Question it. Ask for evidence. Look for alternative explanations. Try to figure out how you might be wrong. This doesn't mean being contrary for the sake of being contrary. It doesn't mean rejecting everything. It means thinking critically, thinking carefully, thinking honestly. I've used this approach for everything in my life. Not just physics. When I was learning to draw, I questioned the standard techniques. I tried different approaches. I experimented. Some worked, some didn't. But I found what worked for me by being willing to question the conventional wisdom. When I was learning to play bongos, same thing. The teacher would show me the right way to do something, and I'd think, why? What happens if I do it differently? And sometimes I'd discover that the teacher was right, and sometimes I'd discover a different approach that worked better for me. This attitude, this questioning attitude, it makes life more interesting. It opens up possibilities. It helps you avoid being trapped by what everyone else thinks. But more importantly, it helps you get closer to truth. And truth matters. Not because truth is comfortable. Often it's not. Not because truth makes you feel good. Sometimes it doesn't. But because truth is real. Truth is what's actually there, whether you like it or not. And in the long run, understanding what's actually true is better than believing comforting lies. When we built the atomic bomb, we had to understand nuclear physics as it really was, not as we wished it to be. Lives depended on it, millions of lives. When doctors treat patients, they need to understand biology and chemistry as they really are, not as they wish they were. When engineers build bridges, they need to understand physics and material science as they really are. You can't fool nature. You can't negotiate with reality. You can't believe something into being true. Nature is what it is. And if you want to work with nature, if you want to understand it, use it, predict it, you have to accept it as it is. This is what science teaches us, not specific facts about atoms or stars or cells. Those are important, but they're not the most important thing. The most important thing science teaches us is humility, intellectual humility, the recognition that we can be wrong, that we're often wrong, that being wrong is okay, as long as we're willing to correct ourselves. This is the opposite of arrogance. It's the opposite of, I know I'm right, and I won't even consider that I might be wrong. It's saying, here's what I think, based on the best evidence I have, but I could be wrong. Show me better evidence, and I'll change my mind. That's not weakness. That's strength. That's wisdom. I've spent my whole life questioning things, doubting things, testing things. And you know what? It's been wonderful. Because when you approach the world this way, when you're always asking questions, always looking deeper, always trying to understand, the world becomes endlessly fascinating. Every answer leads to new questions. Every solution reveals new puzzles. Nature is like an onion with infinite layers. You peel away one layer, you find another underneath. And that's beautiful. That's exciting. That's why I say the pleasure of finding things out is one of the greatest pleasures there is. But you can only experience that pleasure if you're willing to doubt, if you're willing to not know, if you're willing to question your own assumptions. The person who thinks they have everything figured out, they stop learning, they stop growing, they stop discovering, they've killed their curiosity. But the person who knows they don't know, they're alive, they're engaged, they're learning, they're growing. This is what I want you to take away from this. Don't be afraid of not knowing. Don't be afraid of being wrong. Don't be afraid of doubt. Doubt is not the enemy of knowledge. Certainty is the enemy of knowledge. Premature certainty, the belief that you've figured it out when you haven't. Doubt is what keeps you honest. Doubt is what keeps you learning. Doubt is what allows you to actually discover things rather than just confirming what you already believe. The key to science, the real key, isn't complicated equipment. It isn't advanced mathematics. It isn't knowing a lot of facts. The key to science is simple. Question everything, test everything, be willing to be wrong, and never ever stop doubting. Because the day you stop doubting is the day you stop doing science. And science, real science, honest science, curious science, that's one of humanity's greatest achievements. It's how we've learned to understand the universe. It's how we've learned to work with nature instead of just being at its mercy. But it only works if we maintain that spirit of doubt, that spirit of questioning, that spirit of intellectual honesty. So question things, including what I've told you today. Don't just accept it because I'm Richard Feynman and I won a Nobel Prize. Accept it because you've thought about it, examined it, tested it against your own experience and reasoning. And if you find something wrong with what I've said, great. Tell me, show me. Let's figure out the truth together, because that's what science is. That's what it's always been. Not a collection of facts to memorize, not a set of authorities to believe, but a method, a process, a way of thinking that starts with doubt and ends with understanding, the real understanding, the kind that comes from actually engaging with reality, not just believing what you're told. That's the key to science. That's the key to everything.